Okay, so chapter 5, the reclassification of prime and composite numbers. So prime numbers is an obvious place to go to use the mod 9 lens to see what we can find. Is there a regularity to them using mod 9? And what I discovered that the classification of prime numbers does not, in fact, provide a nice orderly pattern, as one might hope and expect, given everything else we've seen. That is, if you look at it in the way that people are looking at it currently, in terms of getting the families right. And that should become clear in a moment. So essentially what I did, because I'd seen that there were these 6 octaves in music that repeated, I kind of got the idea that each number was an octave. And so I wrote the numbers out, just the numbers that we have, in 6 columns, 1, 2, 3, 4, 5, 6, and then the next line, 7, 8, 9, 10, 11, 12, etc. And then I converted using the mod 9 lens to see that all the primes, bar the 2 and 3, and we'll come back to them, but all the primes occurred in the first and fifth column, and very specifically used one of the number groups in the first and another in the fifth, namely being the 174 and the 528. So that was immediately interesting. So there's no 3, 6s and 9s for mod 9. Now, of course, we've got 2 and 3 to deal with, but we'll come back to that. So you can see here all the red numbers are in fact prime, and then there are some other numbers in the strings that contain any primes, and numbers like 25 and 35 and 49. So these numbers, when we factorize them, 25 is obviously also divisible by 5. So strictly speaking, according to the definition of a prime, which is a number that is only divisible by itself and 1, here it has another factor, which takes it into what is traditionally the composite number sequence. So normally you'd find the 25 in the composite number sequence. But what I'm saying is this, is that primes that are larger than 5, the numbers that appear here with all the primes are this part of the same family, because as he just uses the simple logic that if you disagree that a number like 25 should be involved with the prime family, it's rather like saying that the congress of 2 humans would produce anything other than a human. So that's the simple logic behind it. And then later on we'll understand why it's important that we understand that 25 is in the prime family and not the composite family. So what I did was to look at the composite numbers, so the accepted composite number sequence beginning with the number 4, 6, 8, 9, etc. And again, looking for something that was regular in terms of a repeating mod 9 sequence. Again, I couldn't find one, but you can see that it's trying to get to something regularized. And then when I applied this family classification, then everything comes clear, because when you do that, you see that there's a regular 12-digit recurring sequence, which includes those pesky numbers 2 and 3 in the composite family. And we can see that because later on in the sequence, we see it begins 2, 3. And further down 2, 3, 2, 3, 2, 3 all the time. So that tells you that 2 and the 3 should be in the composite family. And then you've got this 12-digit sequence, you split it up into 3 4s, and you see the number groups as we've seen everywhere else. So we can be pretty confident that that is in fact the correct composite family sequence. This one, not the one we currently use. And further, when you can break that down into 2 6s, you see the 1 2 4 8 7 5 and the 3 6 0 3 6 0. So obviously when you apply the rules to the prime numbers, and you include 1 as the first prime because the next one is 19 and that's also a 1. So we can say that it's going to be 1 5 7 11 13 17. And it produces a 6-digit recurring sequence that again shows the 3-dimensional numerical symmetry, and the 174 and the 528. So in terms of a visual understanding of this, I used a square of 9 number spiral. So the numbers just spiral around and around and around. And I was doodling, and I just started crossing off all of the numbers that were in the prime family. Not just the primes, the prime family. And I found something quite extraordinary, which plays into something called Ulam spiral, which is this next visual. So this is just a very much larger representation of the square of 9 spiral we see above. Now you can see that there are diagonals that are almost forming. Now, if you use my classification, that turns into this, which is perfectly regularized. Now imagine coming from underneath and pressing upwards on the 1 to create a pyramid, or pressing down on the 1 and creating a vortex. And notice the southwest diagonal, where you don't have the structure of the rest. And it's interesting to note that all of the numbers here are exponents. They're the squares of prime numbers. 11 squared, 13 squared, 17 squared, 19 squared. All lie on this southwest diagonal. Now, interestingly, if you do think about it as a pyramid, there is a pyramid which at the solstice makes it appear as if a snake is slithering down one of the sides. Just like that looks like a snake slithering down one of the sides. And notice the 4 quadrants. And I've put these sort of fish eyes. I sort of see them as fish eyes, and the fish swimming to the right, upwards, to the left, and down. So, what does this look like? It looks like a square pyramid. So, but there are square pyramid numbers. And here's the sequence for the square pyramid number sequence. See, I think this is the number sequence that underpins prime numbers. And this one gives you a 27-digit repeating sequence. So you can't obviously split it into 2, but you can split it into 3. And we see the 174, 528, 369 again, which is ubiquitous in every number sequence that you can care to look at. Any non-man-made one, so any natural number sequence. So here, the 27 digits is obviously centered on the 13th term by this number 819. And that is a very important number in my great friend John O'Leaf's work. And we'll come back to that later.